Alrighty, welcome, everybody. Today, going to be running through our review of axisymmetric and torsion problems from the homework, and that's going to set us up for our second exam on this Wednesday. Right. So the files should have gone out at the end of last week, and you got a notification about those. So hopefully you've had a chance to just take a glance over the results. But we're going to go through them all, and if you have any questions along the way, then feel free to just shout out. All right, so let's start out with our torsional problems. Here, we're just going to use our circular bar theory. We're replacing a gas turbine propulsion shaft. Max torque is going to be 12 million inch-pounds. And our maximum shear stress for the material, we want to keep it under 15 KSI, so 15,000 PSI. Because of our bulkhead cutout limits, our outer diameter of the shaft can't exceed 20 inches. So we're pretty much capped at a 10-inch outer radius for the shaft. And we want to find what's the minimum shaft thickness, or what's the biggest we can make the inner radius in order to carry the load. All right. The thinner we make it, the less expensive it's going to be, and also the less it's going to weigh. All right, so it's kind of an optimization problem where we've got a limit on the stress. So we know from our basic circular theory, tau max is going to be torque times max radius over J. Since our max radius occurs at the outer edge, that means we can fix that R in the problem. So R max, no matter what we make the inside radius, the outside radius is always going to be the biggest one. So we can put in our max stress at 15,000 PSI. And our R max, regardless of how we thin it out, is going to be at 10 inches. And we know our applied torque. So what we could solve for is the J that's required. It's 8,000 inches to the fourth. Right. And for a hollow bar, we just take pi over 2 r squared for the outer minus pi over 2 r squared for the inner. So that means if our r outer is fixed, we can solve for the r inner. Comes in at 8.37 inches. Or we're going to need to make this drive shaft 1 5/8 thick. So basic circular torsion theory, and what we work toward in this one was getting a J value that would keep our stress at that lower level, the 15,000 PSI. And then once we have the J value, if the outer's fixed, we just work on finding that inner radius. Anybody questions about that? All right, let's jump over to the next one. So here we're looking at a two-part shaft. We've got multiple torques on there, and we've only got one support, which means this one is going to be statically determined. We want to figure out what's the max stress in each one, what's our torque that's carried in order to get that, and then our angle of twist at points B and C. A is going to be our fixed end at the back there, so that one's going to have no rotation. And here we got our properties for each one. So in order to grab those for, let's bring up our torsion summary. That'll give us a quick way to grab all the equations we need. So according to our torsion summary, here's our multi-bar. Twist angle, TL over GJ for each one. And then we can just use a series of free body diagrams to get what we need. So for that first cut, if we want to figure out what's the torque in bar number 1, I could take a slice right here, keep the applied end that's got the two loads, and then the internal load T1. So we can calculate that one, comes out at 25 kip inches. For bar number 2, we can just take a slice off the end right here and keep that end. We could see that one's actually going to carry -5. We could look at that on the front end and see it's going against our counterclockwise rule. And on the back end with our T2 going in the about -Z direction, we can also see their same direction. So T2 is going to have to come out That means bar number 1 is going to twist counterclockwise, but bar number 2 individually is going to twist the other way. Stress is just TR over J. And remember to be careful that we're using individual subscripts on all of these. All right. So the torque carrying number 1, the max radius on bar number 1, and then J for bar number 1. And same thing for number 2. We get 589 and minus 398. Note that although the torque is a lot bigger on the first one, the stresses are closer because we've got a much bigger J value in the first bar. And then finally, we can figure out what our angle of twist is. So for that first bar, that's going to twist 5.13 10 to the minus 4 or 513 microradians. That's going to be counterclockwise because we have a positive sign. And that's also the twist at the middle because we were fixed at the back end. For bar or for point C, we've got to incorporate both the twist from bar 1. 2 is going to go along for that ride, and then 2 is going to twist back some. So we take the number we already got, then we add this twist for bar number 2, and we note that the net actually comes out a clockwise or negative twist at the end of that dual bar structure. So even though we were carrying a much bigger load in bar number 1, because bar number 2 is fairly flexible, it was able to rotate more in this TL over GJ value and get us back to a net clockwise rotation on the end. So everything that we saw on the statically determinate page in action. Anybody have any questions about that stuff? All right, let's try a statically indeterminate problem then. Got a 3-bar linkage. We've got an applied torque in right here. And then we've got fixed ends here. So if we want to look at the torque carried by each shaft, we're going to need to find out T1, T2, and T3. Max shear stress, once we get that, that's pretty easy. And then angles of twist at both of those intermediate spots. Okay. And we've got all the properties for those. So we're going to need a pair of free body diagrams. If we take one slice at this first intermediate point, that's going to involve T1 and T2 and the applied load. So we got an equation with 2 unknowns. Then we take another slice here at the second intermediate point, and we can see that T2 is just going to equal T3. If there's no load between bar 2 and 3, they're going to carry the same amount of torque. So that's 2 equations, but 3 unknowns. So we need one more equation to work that out. And we can get that from angle of twist at any location we'd like. All right. So if we're thinking about a 2-bar, here we go, 3-bar linkage, we could count up the angle of twist at B. We know that's the twist at number 1. Or if we come at it from the front end, I can go this and this. Bar 3, if I hold it in the front, is going to actually twist clockwise on the back end if I stick my thumb on the back end. And likewise, bar 2 relative to 3 would twist clockwise. So I can say that at B, my twist is either going to be number 1 or it's going to be the negative of 2 and 3, because both 2 and 3 on the back end will twist the opposite. We could also think about it at point C. 1 plus 2 from A to C will get me the twist angle. Or if I go from D to C, I'm on the back end minus on 3. Or I could look at all 3 together and I could say 1 plus 2 plus 3 has to come out at 0 on the fixed end. All 3 of those equations are just the same thing, rearranged, right? 1 equals minus 2 and minus 3, 1 and 2 equals minus 3, or 1, 2, and 3 equals 0. All right, so you just move it back or forth and you're at a different spot on it. But all 3 of them have to sum up to 0 since we're fixed at both. So that's going to be our third equation. This is what's going to let us get to the solution. All right. So I just set it up at B here, but again, 1 plus 2 plus 3 equals 0. And then we can substitute in from above. So I could solve T1 in terms of T2. I could solve T3 in terms of T2. And now I've got an expression just for T2. Likewise, you could do it for any other substitution order you'd like. But T2 comes out minus 616 Newton meters. T1 comes out at 4,300 and T3 at minus 616. So if we take a quick glance at those, sanity check, T1, bar 1 is carrying most of the load, and that's where that 5,000 is applied, right at the end of bar 1. And then 2 and 3 together are carrying the same load end to end, and it's a much smaller load, 616. There's a much longer length, and remember for our stiffness, GJ over L. So the longer we make the bar, the easier it is to twist it a given amount. We've got a short, stubbier bar for number 1, so it's going to carry most of the torque, and then together those two make a pretty long bar for 2 and 3 where there's no intermediate load, so they're not going to carry as much of that. Then for the stresses, just TR over J. Remember to be careful and use only your local values for that particular bar. All right, so whatever the max radius for each one is, we plug in. There we get our stresses. And then angle of twist. At point B, we can either do 1 or we could do negative of 2 and negative of 3 added together. Either way, we're going to get 0.119, and that's going to come out in radians. All our units should cancel off, so we're left with a radian angle. And then at point C, we can either add up 1 and 2, or we could take the negative of the twist angle for 3. So TL over GJ, all with 3 subscripts and a minus, might be a little bit faster. We get 0.0061 or 6130 microradians. We could have also added 1 and 2 together, twist angles to get that intermediate. So that's an option for us. We can see that here in our indeterminate. We can get 1 or minus 2 and minus 3 at B. And then at point C, we can do 1 plus 2 or minus 3. Should come out the same. All right, so that gives us a chance to try all of our circular torsion. We did the statically determinate, statically indeterminate, multi-bars for both. And then we did an optimization with a single cross shaft. All right, let's take a look at number 4. And here's our chance to try out a composite cross-section problem. So we've got this cross shaft transmitting torque from one side to the other. If there's an engine failure, that's what the cross shaft's job is. And we're looking to try out a new composite material one, a thin sliver of titanium 6-4 on the outside. It's more expensive, it's denser, it's got a higher stiffness. So we put a little sliver of that on the outside where we know the torque is going to, or tau, the shear stress, is the highest. And then on the inner, we put some 2024 aluminum. That can still take some of the load, but at a smaller magnitude, and it's lighter weight, and it's got a little bit more flexible stiffness. Now, this is a special case of statically indeterminate, where instead of adding up angles to 0, we push them all concentric with each other and coaxial. So instead of having angles add up to 0, they're all going to be the same angle. We're going to say that each of these rings in here carries some portion of the overall torque. So 1 and 2 are each going to carry their share of the torque based on the stiffness and the properties. And then the angles of twist will all be equal. So phi1 equals phi2, phi1 equals phi3, etc. That's n-1 equations. And then this torque sum is my last one. So I have enough to solve for all of them. And in fact, if I plug these in here, I have a shortened closed form right here. Torque in any member is going to be the total torque, and then GJ divided by the summation of all the G times J's that we have. So this one for the specific component we're looking at, and this for the whole thing. Remember, our stiffness, our torsional stiffness, our torque per twist angle is GJ over L, but it just happens that when it's composite, they all have the same length. So the over L cancels off here. And this is what we're left with. Basically, it's the local stiffness over the overall summation of the stiffness. So we can plug and chug with that formula. We get J for each one. Here's our torque sum. Here's our angle of twist. We just combine those into that closed form formula. And I see that the number one section, that's the titanium outer section, is going to carry 259,000 inch-pounds. The inner aluminum section is going to carry 365,000 inch-pounds. Wait a minute, that was supposed to be the stronger part. We can have a relative amount of torque that's carried be larger on the inner one, but the stress still be lower, all right? Because of our radius and our J value. So J for that inner aluminum, because it was 3/8 of an inch thick, is pretty large. Our 1/8 inch thick on the outside ring actually has a little bit less J value and also has a higher radius. So bigger max radius and a thinner part leads to us having about almost 40 KSI in the titanium. And then in the aluminum portion of the ring, remember, we can only go as far as aluminum goes, so only 2.875 or 2 7/8 there. That's going to max out at 22. All right, so almost half as much stress in the aluminum. That's what we're going for. The aluminum's cheaper, so we can have it make up more of the part, and it'll still carry a lower stress if it's the inside piece in this case. And then for our twist angle, we can look at 1 or 2. Either one will twist the same because that's how we set it up. And both comes out at 1.95 radians. All right, so to put that in perspective, it's 120. It's almost a third of a rotation. That's how far out of phase the blades will get as that torque is sent over, assuming there's not a reduction at the gearbox. Anybody have any questions about that composite cross section? All right, let's look at one more here as we cross into thin wall territory. We're going to try this out for a cross section, 2,000 kip inches. All right, so 2 million inch-pounds. And then we've got one that's just about 11 to 1. We've got 11-inch inner radius, 12-inch outer radius, meaning an inch thick on the thickness. So this is right at the border of what we can go to our thin wall assumption for, right? 10 to 1, 20 to 1 is one of those or the other is usually our lower limit. So we want to calculate shear stress at the midline for the circular case and the angle of twist. And then we want to calculate the thin wall approximation, which assumes a constant stress across the cross section. All right. So that's why we'll look at it for the midpoint on the circular one where it varies from inner to outer. So in our circular bar theory, stress is distributed something like this. We've got some value at the inner edge, and then it goes up a little bit to this much on the outer edge, and we have a little bit of a distribution. It's 1 inch over 11, so it's not a lot. So that's what our circular theory looks like. We're going to take the middle number for that, and we'll compare that with the thin wall torsion, which, remember, we just assume is a flat distribution across that narrow thickness. So we'll compare the midline of this one with the constant value for that. We'll see how close they come out. So circular bar theory, if I put it in at 11.5, I get 2.40 KSI, and I get 1.82 or 18 microradians per inch for the twist per length. Now, my thin wall theory says I box in the midline. So here's my mid area, 415 inches squared. My torque over 2 times that mid area gives me my shear flow. So shear flow at 2406. And then my thickness at 1 inch. So we divide through there, and I can see that's going to come out to three significant figures at 2.41. So just about on target with our circular bar approximation. And then for theta, we've got to do Q over 2 times that midline area times G. And then we integrate ds over t, which we said we could just make into a summation. So I've got basically one side on a circle. I go around 2 pi r divided by the thickness. Integral ds over t can just be a summation of length divided by thickness for however many sides we have, or one circumference for the circle. And that one comes out exact to 3 figures with the thin wall to the circuit. So what I wanted you to see here is that even down at 11 to 1 or 11 and a half to 1, we're really, really close between those numbers. So anything above that, we can be pretty confident that the thin wall theory is working good for us. All right, here we're looking at the uptake space for a diesel generator. Between 03 and 05 levels, the cutouts for this pipe to come through have a misalignment of about 2 degrees. Right? 2 degrees on maybe, say, 20 feet between levels up there. So it doesn't sound like that big of a deal, but you decide you're going to check it out anyway. So we want to figure out what's the shear flow that's being carried if we force this into place. Say we start with a straight pipe, but the end of it is misaligned for the cutout. So we've got to twist it into place. Now, how you'd likely get that is not by taking a giant torque wrench and twisting with millions of inch-pounds. What you're going to have to do is put in the bolts kind of loose in a few places and then start torquing them down until this aligns with the hole. There's another reason not to use flat oval exhaust ducts and round ones, because you can't misalign a round hole, right? It's always aligned. As long as it's translationally aligned and it lines up from here to here and here to here, you're okay. You don't have to worry about the angle. Drill the holes after you set it up. So we want to figure out how much torque we're going to have to get from installing these bolts and torquing them down and twisting, and then what residual stress will be carried in that duct afterwards. So here's our ramp around. Oftentimes, if we're starting with a thin wall type problem, we can just assume our dimensions are going to be midline. That'll make things a little bit easier for us. So our flat section is going to be 19 by 24, and then we've got basically a rectangle of that. And then if we put the two ends together, we're just working with a circle for the rest of that enclosed area. So a whole circle pi by r squared plus diameter by the flat width rectangle, and we get 908 square inches. Right? We convert that phi angle into radians. We get 0.0349 on the radians. So that takes care of the units for us. Our twist per length is going to be that little number divided by 240 inches. And we get down to the 10 to the minus fourth on our twist rate, radians per inch. 1.45, 10 to the minus 4. And then we know our twist rate for the thin wall, Q over 2 enclosed area and shear modulus, and then this ds per t. And what we want to solve for is that shear flow. So we've got all the other stuff. We can fill this in. We're just going to go around 2 flat sides. So those are going to be the 19 divided by 1/8 inch wall thickness, and then the 2 ends, which are going to be pi r for 2 half circles. Or you could just say 2 pi r and have one of those entries. So Q comes out to 3,200 pounds per inch. That's force per length flowing around. The torque that equates to is almost 6 million inch-pounds that it's going to take to get that realigned. Once we have installed it, and remember, we're not going to find a giant wrench. We don't have a wrench that's long enough with a long enough moment arm to be pulling with 6 million inch-pounds, right? No matter who we call, even if we called Andre the Giant and got a 100-foot-long pipe plugged into the end of the torque wrench, we're not going to get this number that we need. So we're going to have to get it by putting the bolts in kind of loose and then torquing them down individually until it forces it over. The stress that we're carrying from that 3,200 pounds per inch, divide that by 1/8, so we're multiplying it by 8, and we get up to 25 KSI. It's 25,000 PSI just from the misalignment. And that's about half of the yield stress or more for that stainless steel material. This is actually a true story. Had a lot of cracking in this exhaust duct on one of the LHDs. And it turns out that the company that designed this original one, and besides having some pulsating Mr. Peanut shapes while the diesel exhaust is going, so it tends to go like this, and this is the vibratory mode. If you take 4522, we'll look at a problem like this, but the vibrational mode goes something like this. So there was a lot of cracking where the flat and the round part interfaces. You probably have seen these in gas turbine exhaust, but that's okay because the flow's pretty constant. So it changes shape and stays that way. But in a diesel, it's exhaust pulse every time the cylinder fires, right? So it's kind of reciprocating, goes back and forth like that. Whereas in a round duct, I'm starting with this shape, and my deformed shape is just going to be, still round. There's no concentrations to it. So let's see. That all turned out pretty poorly. Oh, so the punchline I was going to get to, the company that designed the original one is the one that they hired to redesign it. And they put it in another flat oval with even more stiffeners, and then it cracked more. And then finally they went back and thought about doing a round, which is pretty standard for modifications and repairs. Anybody have any questions about that? All right, good lessons learned. Let's go on to this one. All right, we're looking at a section of flight deck from EPF. We got a corrugated type structure on this one, and here's some dimensions. All right, so we've got a top plate, a bottom plate, and then we got some webs, which are a little bit thick. All these dimensions we're going to say to midline, and they're all based on this fairly easy 3-4-5 triangle setup. 60 on the half triangle bottom, 80 there, and 100, so it's a 3-4-5 type shape. So this time we're going to be looking at shear flows in 3 sections. We got Q1 going around here, we got Q2 going around here, and we got Q3 going around here. Also note this one is fully symmetric down the middle. So whatever I get for B should be the same as for K. D and F should have the same magnitude. C and H should have the same magnitude. Well, L crosses the line, so it's automatically covered there. And we'll get what's called a skew symmetry. So if it's going down and to the right on B, it's going to be going up and to the right on K. And also Q1 and Q3 will have to be the same. Q2 equals Q2, so we're covered on this middle one across the symmetry line, but Q1 and Q3 will also have the same magnitude. So we'll see how those work out. Here's all our properties. Midline area, even though they have different thicknesses, is going to be the same for all those. So 4,800 millimeters squared. Twist rates for this multi-cell problem, just like we saw in the class example, same twist rate. We're going to assume that it all twists together. So we can pick any of those three, any two of those three. All right, so let's say we do 1 and 3, because of symmetry, I'm going to be able to cross off a lot of stuff. Same areas, same shear modulus. We just need to go around those loops. So my loop for number 1, I just need to travel around it. I'm going to start on the top and we go counterclockwise. Right? So I need Q times S over T, and the Q has to include any and all that are traveling through down. So I got Q times 120 over 7. That's going to be going across our top here. So let me do blue color here. I'm going to go this way. Just has Q1 and then 120 over 7. I come down here and I've got 100 over 3 and only Q1 traveling in there. So that takes care of this one here and this one here. And then lastly, I need to go up the web to complete the loop. So I'm going to be going up this way. Note that if I take this loop and I started and ended right here, I got to go counterclockwise the same way on all of them. I go across the top down here. All those were just with Q1, and here I'm going with Q1 but against Q2. It's going to be Q1 minus Q2, and then that 100 divided by a thickness of 3. Right. So that takes care of everything around that loop. And the second one, also start going over the top. So let's do maybe orange. Need something that's different than both. How about green? So I'll start at this corner, same upper right corner. So I got the top with only Q3, 120/7. Then I come down here, I've got Q3 minus Q2, 100 divided by 3 thickness. And then I can come up this side, I got only Q3, and I got 100/3 also. So there's those parts. I can work that down. The Q2 is actually going to cancel out, and what I get is Q1 equals Q3, which we said had to be true, bless you, due to symmetry. All right, so we've got that one out of the way. And then we need just one more from 1 equals 2 or 2 equals 3. All right, I'm just going to do 1 equals 2, but you get the same result either way. So we again do those loops. The half, the median area, and the G cancel off. So we're just looking at the QS over T summation. There it is for number 1. And then for number 2, I've got 2 webs. So I've got this one and this one working with 2 minus 1 and 2 minus 3. And then I've got the bottom this time, 120 going across there, only Q2, and then a thickness of 4. And by the time we get all the rearranging and substitute in 1 equals 3, I get a ratio between 2 and 1 right there. So Q2 is a little bit bigger than Q1. Then I could throw those into the torque summation at the end here, and I could finally solve for a single. I said 1 and 3 were the same. 2 is a multiplier of 1, so we'll just change it all to 1. We get Q1 comes out at right at 330 Newton per millimeter, or 330,000 Newton per meter. That also equals Q3, and then Q2 a little bit bigger at 382. So now I've got my shear flows for each one, and then the stresses are just going to be Q divided by thickness. So we've done almost all the work for that. Generally, when somebody doesn't give you a diagram with arrows, if they do, you just follow the arrows. But otherwise, you want to look at these two numbers. If 2 is bigger than 1 for the Q's, just point the D arrow that way. All right, and 2 is a little bit bigger than 3, so I pointed F and D in the direction of the larger one. So it just makes all the torques positive. Kind of helps you to visualize also which way the shears are flowing all the way around for those shear stress towels. So we crunch through there, we get all our stresses as labeled on the bottom there. And finally, our twist rate. We can do that on any of the 3. Probably one of the outboard ones is a little bit quicker to do, but should all come out the same. We get right around 60 microradians per millimeter. Or if we don't do it on a per meter, it's going to be 060 radians per meter. Anybody have any questions about that multi-cell thing? All right, a lot of this torsion stuff, once you get the formulas, it's fairly straightforward. Let's take a look at number 8. We're looking at this T-shaped cross-section for a minesweeper rudder, all non-ferromagnetic materials. So we got a ceramic set of wings on the sides and then a wood main spar. The ceramic wings have a really high stiffness. They're 6 inch by half thick. Wood spar is also half inch thick, but 24 in the long direction, and then a much lower modulus. We've got max torque from a turning rate maneuver, and we want to figure out what is the torque carried by each one, what's the stress in each one, and then our twist per length for that rudder shaft. And if we peek back at our thin wall open, our thin wall open formula is based on some equivalent J for a stretched out rectangle. Stretched out rectangle comes out long times thickness cubed over 3. So basically a third VT cubed. And then our twist rate is T over G times that J right there. And our stress, torque over J times the thickness. So we can see it scales directly with the thickness in the numerator, and then J scales with a cube of thickness in the denominator. There's our total torque. There's our J's for each one. And if we want to look at it for a composite cross section, so this was for a single cross section, our composite section takes advantage of the same ones as in circular. Twist angles are the same, and they each carry a share of the torque. So for same material, we work out these shortcuts. For composite material, we've got torque, G times thickness for that particular piece, and then a GJ bar, which is a composite torsional rigidity. That's G times J for all the pieces added up. Note that that means the one that carries the most stress is going to be a combination of thickness times material property. Right? We had same material or same thickness. It's going to be a half for both. So what's going to determine our share of the stress and load is going to be the difference between these. We see the wood modulus is a lot lower, about 12 times smaller than for the ceramic. So our GJ bar comes in at 14 million inch-pounds. CalMax for material number 1 is just going to be torque times GJ for the ceramic over that 14 million that we came up with, comes up with 103 KSI. That's a really big number. That's toward yield strength for, say, HY100, right? But our high-strength ceramics can accommodate that. Same thing for number 3, because they're both the same material. And then for number 2, the wood spar, we see it's down at 8,000 PSI. That's a much more reasonable number for something that's non-metallic. Organic type of tea. So even though the wood spar was bigger, the thickness and the modulus are what determine the share of the stress that gets carried. And we could see that much more because the higher modulus went into the ceramics, right? 25 versus 2, that's 12.5 times bigger. 8 times 12 is 96, and another half gets us to the 103 ballpark. Any questions about those thin wall opens? We just treat each piece as an individual rectangle and then use our summation tools there. And then last one here, here's our elasticity method problem. This is kind of our segue into 4612 if you took that class later. We did the circle in class. We also did a triangle in class. This one's going to be somewhere in between those in difficulty. We do have a single equation for the whole surface. Here it is. So we can easily turn that into 0, just move the 1 across. Right? And then we've got a couple of useful values for the ellipse. IXX, integral y squared dA is going to be pi over 4 AB cubed. And then IYY, moment of inertia about that vertical axis, integral x squared dA to be pi over 4 A cubic. So if we come across any of these, we can just substitute in those constant values and pi AB for our area. So let's see how these play out. Torques we also got for that one via the summation. You see the ceramics are carrying a good bit more of that. All right, so we got to choose our Prandtl function. Just needs to be 0 all the way around the perimeter. So I could take that ellipse equation, subtract the 1 over, and I got to say this definitely equals 0 on the boundary. So it'll be a constant around the boundary. That's what we have to have for Prandtl. We might as well make it 0. That's the simplest number. And then some multiplier in front. And I know that the del squared phi, or the Laplacian, I believe it's called, it's just second derivative in each direction equals minus 2g times the twist rate. And that's equal to a constant because our theta is a constant. So I can do a partial Prandtl, partial x, do a second derivative, partial Prandtl, partial y, one more derivative. I see that variable parts fall off of that. That's what we want. We want to get down to a constant here. I could throw those in on the left side. Second derivative with x plus second derivative with y. And there's no z in there. So there is a second derivative with z, just happens to be 0. So that takes care of this left side operative. And then we set that equal to minus 2g theta. So I can solve that constant in terms of the twist rate. We're halfway there. I see C1's got a minus relation, and we saw that same thing with the circle. C1 and theta had a minus relation. And then my theta, or my phi here, equation, I've got something now for C1 in terms of twist rate. I also know that if I integrate that Prandtl function over the area and take double it, I get the applied torque. So I can set that one up. A little bit of math in here, but it's not too bad. Once we get to this x squared d area and a y squared d area, and I separate those, here's where I can come in and say, oh, y squared dA, I'll just take bending moment about x. X squared dA, I'll take that bending moment of inertia about y. And we have a number for those for the ellipse. So those can just plunk in here and here. And integral dA, I'll just take area, pi AB. So we avoided any messy integration with those curves, just took the cross-section properties for an ellipse. We can look those up. And we finally work our way to torque equals minus pi C1 times AB. If I now sub in what we had for twist rate, I can directly relate the torque and the twist rate. That's finally getting to something we need. We know the torque, we know the dimensions of the material, and we're trying to get twist rate. So we see it comes out to torque, a squared plus b squared, and then this sum, this product on the bottom. And for a positive torque, that'll give us a positive twist rate. Everything else in there comes out plus. I can also go back now and get C1 in terms of the torque. I see it's going to be minus T over pi AB, or minus torque per area. And here's my function for that Prandtl. If we want to visualize that, here's what it looks like for an ellipse. Just like for the circle, we had it look like this. And remember, our slope all the way around was going to give us our perpendicular stress. So here I had my maximum d phi dy. If I got y this way and x this way, thinking back to the circle, let's scribble this one down. I got x over here, I got y over here, and I got phi on the vertical axis. So my Prandtl derivatives give me my stresses. So here I've got partial phi, partial y. It's going really steep up in y, doesn't have any slope in x. I could see it's flat across this direction. And partial phi, partial y is my tau in the x direction. So that goes right here. And then on the other end, it's sloping down. d phi dy is a big negative number, meaning the stress goes to the left or against my tau in that x direction. And then over here, if I check this one, minus d phi dx is my other stress. That's my stress in the y direction. So if I try that out, here I have a maximum x slope, no y slope, and that's minus d Prandtl dx. So my stress goes against y. And over here, I'm running downhill real fast in the x direction, no slope across the y. So I'm going to get all stress this way, and the sign change points it up. So there I can see it goes around in the circle, just like I think it should. Now, we didn't have to decide what these things were. These were already pre-cooked into that Prandtl form. So anywhere I've got a slope in the y direction, I have horizontal stresses. Anywhere I have a slope in the x direction, I got vertical from the in-plane picture. So we can plug and chug on those. Here I see minus ty over that bottom product, and then t times x positive over this bottom product. So that tells me on the right-hand side, my stresses are flowing up. That makes sense for counterclockwise. If I put in a negative x, on my left-hand side, the stresses are going down generally. So that works out. And then the xc, if I'm on the bottom and I get a negative y, that converts to a positive xc stress. And if I'm on the top of the ellipse, it's got a positive y, so this comes out pushing negative or to the left. Max values are going to be at those quadrant points, and I can see them right here. So if we look on the ellipse, remember, I've got the same height, so I'm getting there from wider apart places horizontally. So here I've got a kind of steep slope and a kind of steep slope here. And those result in these are fairly steep slopes in X, which results in my Y stresses. Minus d phi dx gives me my tau yz stresses, and we can see it's pretty steep. Now I've got to get to the exact same point, but from two places closer together. So my slopes on the bottom and the top quadrant points are going to be higher. This is a steeper slope right here, and a steeper slope down over here on the back, because I've got a shorter distance to cover here. Here I had the same height change, but a longer distance. So I expect these blue slopes to be a little steeper, and d phi dy is direct relation to my tau xz. So my xz stress is going to be real big, a little bit bigger than those red ones, and it's going to happen at this spot and at this spot right here. Those other quadrant points are where the yz maximizes. So it still goes around in the circle, just like we thought, counterclockwise, so that makes sense. And I can see from the picture, my steepest slopes are down here at the bottom and the top of the in-plane. The left and right edge have the max slope in the X direction, but since it covers over a longer distance, shorter distance here, the blue ones will be a little bit steeper. That means they'll get bigger. Okay. And we can see that in the formulas. Last thing is the warping, all right? I know that my warping formula for the circle came out flat. For the triangle, we saw it had kind of a three-way saddle, three-legged saddle undulation, positive, negative, around 6 spots. And then here are dw dx, warping with x and warping with y. So I can integrate up with dx, I can integrate up with dy on these two formulas, and the only thing I might be missing is functions purely of the other variable. Right. So I come up here, I get this plus g times g of y. I get the same thing over here plus maybe something with x. So if I look over to the left, there's nothing with x by itself, so f of x is going to be 0. And if I look at this one, look over to the right, there's nothing with only y here. So g of y is going to be 0. That means this one common term, if it's the only term we see on both sides, then that's all we got. Nothing with only y in here. When we integrate up, nothing with only x. So here's our warping function. A is bigger than b, so if we flip that around, everything in here, in terms of the variables, I have a positive sign. So for a plus torque, it's just a function of our x and y position, all right? We got a minus, plus, everything on the bottom, and then it depends on the sign of x and y. So if x and y are positive, then this whole thing's negative. If they're double negative, it cancels off, and we also have a minus. So in quadrant 1 and 3, we're down, and in quadrant 2 or quadrant 4, our warping comes out positive. So if I plot this equation, this is what it looks like. We've got a saddle, but it's on a 45-degree angle, basically. Okay. Quadrant 1 is this backside droop. And my 0 line is going to go across the center. A diameter line in both ways is going to be 0 warping. So that's going to be across here and across this way. All right. Across the quadrant points of the ellipse. That's no warping. Quadrant 1 is this backside bottom, and the front bottom is quadrant 3. And then the two peaks, the one on the left is quadrant 2, and the one here is quadrant 4 as we come back around to the right side. So there you can see the warping shape. 2 of those quadrants are down, 1 and 3, and then 2 and 4 are up. And that would be the same shape all the way down the axis of that ellipse. We take any slice, it looks like that. Classic Pringles shape or saddle 45-degree angle shape. All right, did anybody have any questions about that Prandtl method? A lot of work to get to the formulas, but once we're there, we just use them as is. and we can come up with the stresses and the warping for any kind of shape at that point. All right, that's a good time to take our break. Let's come back at 5 after, and we'll run through homework 4. This one will go pretty quick. There's only a few problems, and they're pretty plug and chug. So hopefully we'll have us out of here maybe around 5:30 today. But let's go ahead and take a 10-minute break. We'll come back at 5 after and look at the other homework set. And we're back. All right, let's run through homework set number 4, and we'll be all set for that exam. We can head on. So we're going to try running through our formula, which had a common solution for the R theta axes. We were able to do all this in 2D, come up with these equations, right, for radial stress, hoop stress, and displacement. Only have displacement in that radial direction, so no hoop stress displacement. And then we had 3 different end cases. We're going to try each one. Fixed end is going to be our pipe. Free end will be our hydraulics line on the aircraft that runs into a reservoir. And then we'll have a capped end case, which is good for things like pressure vessels and submersibles. So we'll try each of those 3. And then we can run into our press and shrink fits. All right, so first one, this is going to be our fixed end case. We've got a flanged pipe. Anytime you have flanged ends, something like this, or welded, that's going to clue you in that you're probably going to go with a fixed type condition. All right. We've got reinforced longitudinal bulkheads. We can see the stiffeners are on there, so they're not going. So we got fixed ends, 2,000 psi steam through there. We want to determine radial and tangential stresses at the inner edge and at the outer edge, and then our longitudinal stress as well, which is based on our end case. Pipe's going to be carbon steel, so we got the basic steel properties, and A equals 2 inches, B equals 3. And this is very plug and chug. We just need to run on through. We note that between the sigma RR and the sigma theta theta, the formulas are the same except for that minus and plus in there. So we want to calculate both of these values. Go ahead and do that for the R. So for R equals A, write both of these out. If they subtract to the inner pressure, then you know you got both of these numbers right, and all you got to do is change it to an addition instead of a subtraction. And then same thing at the outer edge, we could do the same thing. So let's see how those worked out. Come back up here to the first problem. Our fixed end, out of the 3 end cases, we solve for that one. That's going to mean epsilon ZZ is 0. So we just use our Hooke's law to get sigma ZZ. All right. It's basically a plain strain case in that setup. So 2 new and times the addition of those 2, that's going to get us addition of those 2 times new, and then we've got a 2 up there. So this comes up with our value for Z. If we try the 2 terms at A, sigma RRA should always bring us back to minus P inner. Remember, P inner pushes compressively, and sigma RR is still positive tensile if it is positive. So we got minus 2,000. That matches P inner. So I know that this 1,600 and 3,600 number are good. Now all I got to do is add them. And when I add them, I get 5,200. So I can be really confident in this number because the radial stress came back what it's supposed to be. On the outboard edge, I should be getting 0 because there's no outer pressure. And sure enough, this second term, same first term all the way down. So 1,600 all the way down. Second term here, 1,600 also. So they subtract to 0. That's good. And then for theta on the outside, I'm just going to add those twice, and I'll get 3,200 for my outer hoop stress. All right. So it pays to write those 2 numbers down. Once you know they subtract to the right thing, and we could check it, then we know the addition is going to be good too. These check out, subtract to 0, and I know they add up to 3,200. Note that that first number shows up again even right here. 2 new times that first 1,600 number will get me sigma ZZ also, and some combination of multipliers in front for all those Z cases. So sigma ZZ for the fixed end, 960. Remember that when we've got a hoop stress, here's our original pipe and the ends are fixed. If I didn't hang on to both ends, then the pipe is going to go out in radial direction, right? We're pushing in on it from the inside like this, all angles around here. And for my Poisson effect, if I wasn't hanging on to the right side edge, it would get shorter as well. We're stretching it out. That soup can label only has so much material. So if I'm stretching it out radially and in the hoop direction, then it's going to have to come in a little bit in Z. Because I'm stuck here where I had it originally, that means I'm going to have to pull with a tensile stress, bless you, to get it back to the original spot, right? It's got to stay right here. So sanity check says I should get a positive stress. If it's inner pressure, it's going to expand radially and it's going to contract in the Z direction, and I'm forcing it to stay at the same position. So I've got to pull back on it to keep it there. So that looks okay. Any questions about that? All right, let's try number 2 here. We're looking at a hydraulic line. Got 1/2 inch inner radius, 1 inch outer, so very, very thick walled vessel there. We want to check out the stress state. The ends go into a reservoir, and if there's a O-ring or grommet there, then it's free to expand or contract at the ends. So we're going to say expansion relief on the ends, meaning no constraint for at least one. And then our material, 2000 series aluminum, we got the properties for that. We want to figure out radial, axial, and hoop stresses at location of max stress. We've seen in all our examples that max stress, regardless of whether we're pushing on the inside or outside, ends up coming in for the hoop stress at the inner edge. So we'll check these at R equals. And then get our axial strain along the line. We're grabbing our free end special case right here. So sigma ZZ is 0, and from our Hooke's law, we can figure out epsilon ZZ. Instead of this time E times those, or nu times those two positive, it's minus nu over E times the summation of those. The minus and plus terms cancel. So again, we end up with that first number that we calculated before, that constant number. So it pays to write that one down, and then times minus 2 nu over E. So if we plug and chug that one together, I got 5,000 PSI on the inside. My radial stress is going to be the check. I get 1667 for the first term, and if I plug in A here, I see that cancels off, and I get 6,667 on the inboard edge for that second term. So if I subtract those, I come out to exactly 5,000 compressive. That's what my pressure was. So I know both of those numbers are good. Now all I got to do is flip the sign to a plus, and I get 8333 for the hoop stress. And I've got a tensile number on that one. Of course, we're pushing from the inside, so we expect it to stretch. That means it's going to be pulling tensile around the hoop direction. All right. No stress on the free end case. If at least one end is free, no way to build up a load. And then epsilon ZZ for the free end. We're going to drop that off. We get minus 2 nu over E, right? Times that same 1667 number comes in right here, and we multiply it by our material properties. We see we get minus 110 microstrain, all right? A negative strain value. That pretty much matches up with what we drew here. If we don't have the right end fixed, it would naturally go to this blue shape. In that case, our strain is compressing in that Z direction. If we're not hanging on at the end here, then from the unloaded spot, if we push out on it, the blue's going to shrink back in the axial direction. And that's what we got. So that passes the smell check as well. Any questions about that free end case? All right, let's go to the last one, which is our capped end case. We're looking at the submersible here. Pressure hull is HY100, and it's 6-inch thick. So we got 30-inch inner radius, 36 on the outside. Here's our basic properties. And we've got hemispherical end caps. Our factor of safety is going to be 2, so that means we don't want to let any stress go above a magnitude of 50,000 PSI or 50 KSI. We want to figure out what's the max external pressure that we can support. Obviously, with submersible, we're going to have open the hatch at the surface, 0 gauge pressure inside, and then as we descend, we're going to build up our pressure. So figure out how much pressure can we withstand before the max stress gets to 50. And then we can convert that to a depth with this gamma times depth equals pressure from our 2201 fluid class. Then we want to calculate what's the radial shrinkage and axial shrinkage in that cylindrical section at the outer edge of the hull. So let's see how that one works out. 50,000, there's my limit on the stress, all right? We know that the largest stress in all the cases we've looked at is sigma hoop or theta theta stress at the inner radius, all right? And it is going to be compressive because we're pushing in on it from the outside. So with P outer, everything turns with a minus sign. So we're going to put minus 50,000 for our allowable stress. And then we know we're looking at the inner radius, so we put in A for R in that second term. First term's a constant. And then we just solve for the P outer. P outer comes out 7,600 PSI. And then I can convert that to a depth. That's 201,000 inches. Might not mean too much to us, but we convert feet, 16,000 feet, which is a reasonable deep diving submersible depth. That's about like what Alvin, the one I drew in the picture or tried to make it look like, would dive to, about 15, 16,000 feet. That covers most all the places in the Atlantic. Enough to recover hydrogen bombs that fall into places and explore hot vents down around the mid-Atlantic ridge and trench and things like that. Now we want to figure out some displacements at the outer edge of that pressure hull. Radial displacement, it's going to shrink by 0.048 inches. So it's going to go down, not too bad, somewhere between 16th and the 32nd, somewhere in there, maybe ballpark. So not too much. But remember, it's a 6-inch thick steel pressure hull. Sigma's easy for the captain. Right here, plug and chug, we get minus 25,000 PSI or 25 KSI for the captain case. Epsilon's easy. We have all the stresses active. It's not fixed end, it's not free end. So epsilon's easy just uses our full Hooke's law. We take the ZZ for the cap formula. That just came from a free body diagram. And then here we plug in our sigma RR and sigma theta theta. Remember, when we add those together, the function of position disappears, and this is a constant. So that works out. We get negative 3.5 times 10 to the minus 4. And our axial compression along the 60-inch cylindrical length is going to be minus 0.021. And remember, for the captain case, it doesn't matter what our shape is for the captain. We get that formula by examining a cut section, all right? So if I take a little slice here and we make a free body, I've got the hull here. And remember, we're cylindrical. So the area that is going to be carrying the sigma ZZ is going to be right here. So sigma ZZ will be the same value all the way around right here, right? And I can see that's going to be a difference of pi b squared and pi a squared, just the area of the metal that we cut through here. On the other side, I could have a really complicated pressure that goes something like this, where it's in all directions on the cap. But what I need to do instead is I just take a little, take a little section of water and fill it in right here. Obviously, very briny salt water with this greenish color. Meant to grab blue. But it can have that hemispherical shape end here. Imagine this is a cylinder head for a Hemi engine, all right? It's hemispherical on this one side, and it's a flat cylinder over here. So now I can just apply the pressure over a pi b squared on this side, all right? And it's all just in the axial direction. So that's how we come up with sigma ZZ for the captain. It doesn't matter what shape the cap is. We could just spill some fluid around it and include that in our free body. Then everything out of the page or up or down cancels off, and we're just looking at the axial. So that's good for any shape. All right, did anybody have any questions about that captain case? All right, last two problems and we'll get out of here. I can see people are nodding off, so that tells me it's time to go. All right, dry dock availability. We want to add a cooling fan down in the engine room. We're just going to slip a pulley onto this existing accessory drive shaft. So we don't need a whole lot of torque. We just need to install it on there. We've got a pulley here. Shaft is going to have a 12-inch inner diameter, 14 outer, so 1 inch thick. And our pulley is going to be 20-inch outer diameter and 14 on the inside. Remember, approximately the same dimension at the interface there. 1 inch wide, so we just need to run a little belt pulley, or the hub section doesn't need to be that long, right? We've got a friction coefficient between the two parts, same material of mu equals 0.2. And then our interference is 1.5 thousandths of an inch. So we got a couple options for this. We want to figure out what the interface pressure is and then the displacements of each part. How much do they have to move? Note that the shaft is a little bit on the thinner side. The pulley is fairly thick at that interface. We could hire Triple H to do it with a sledgehammer. That means we're going to need to calculate the install force to overcome all the friction between the two parts. Right? Once it's on there, we'll probably have more than enough torque to transmit for a fan. Or the other possibility, what if it gets moved to Monday night? There's a delay at the shipyard. H has to do his creative directing on Raw, and we're going to have to do it ourselves. So the other option is we could take it up to the mess deck. We could find a culinary specialist, throw it in the oven for a little while, and bring it up to a certain temperature. A little past that, throw it in the Domino's heat wave box, and run it back down with some welding. So we see what kind of temperature delta do we need to just slip the pulley on and not need Triple H or his sledgehammer or pre-retirement year John Cena, the never give up Cena, not the one that tapped in the last match. So let's take a look at our two options here. All right, for number 4, same pressure. We have that shortened formula, 680 psi. We can throw that one on there. With 680 psi of interface pressure. It's not a super high interface pressure, but we only had 1/1000th of an inch interference, 1.5. The inner part is going to come down just about 1/1000th of an inch, and the outer part's going to come out by 1/2 of 1/1000th. So these are both pretty small numbers. They're closer together than we might have seen in other examples because, again, that inner part is a bit thinner than the hub. All right. We check our difference of those two displacements. It does come back to our original interference. So that's how we know we got the pressure correct and we got these two correct. Option 1, if we use the Triple H approach, we're going to have to install with about 6,000 pounds of force. All right, that's quite a bit of install force. We're going to have to open up a couple of the hatches, and he's going to have to jump from a few decks up and then land on the announcer's table. Right? But once it's on there, we can carry 41,000 inch-pounds of torque. That's way more than we need to run a fan. We could probably run some accessory generators off of something like that. Other option, if we're going to do it ourselves, we can't get Triple H, we can't get Cena, we can't get Umaga or any of those folks to come by. We could just heat up the part instead. Or Great Khali, or et cetera, et cetera. So our delta T just needs to take care of that interference, all right? Alpha delta T is my strain. Strain times the radial distance will give me the amount of displacement we move. So alpha delta TR is my displacement, and that just has to equal what our original interference was. So we see it, we only need to heat it up by about 42 degrees, all right? So if it's maybe 100 down in the engine room on a bad day, we heat it up to 150 or so, that'll be enough. We'll probably want to heat it up more because it'll take a little bit of time to bring it back down. But that's a very reasonable number. We can certainly cook the pulley in the commercial ovens on the mess deck to that. All right, any questions about that? So we looked at press fit for same material there. So here's our press and shrink fit, same material. We can't cancel as much out in that displacement equilibrium for different materials, so we have a little bit longer expression going for this last problem. Here we're looking at Hilo Squadron, we're changing out this bearing sleeve. It's not a bearing in the sense of ball bearings or roller bearings, but it's just a material that absorbs friction and eventually gets replaced. So you have a really expensive titanium rotor hub in the H46-3 or 5-7 on your H53s, but it's an expensive cast part and we don't want to do any damage to it. So when we warm up the aircraft, every time at the start, those rotor blades are going to go from droop to up a little bit when it starts producing lift. And that's sliding between the pin and the hub. Now, the pin is easier to replace, but it's still expensive. And we don't want to cause any damage to either one of these expensive parts. So we slip a little sleeve, we call it a bearing of aluminum in there. It's a softer material, so it will wear away while the titanium stays there. And when it gets worn away enough, we just put a new one in. So to get it out, it's already damaged. We don't worry about it. We're just going to force fit. And that works whether we're installing or removing. We still got to push it the same distance across that frictional surface. So we got U equal to 0.1 and all the properties for both of them right here. When we install the new one, we don't want to damage this soft little sleeve. We want to keep it good for being a wear item in the future. We don't want to dip that titanium part into liquid nitrogen or put it in a deep freezer because that could cause uneven cooling. It could cause residual stresses, and then we could crack the really expensive part. On the other hand, this is a really thin sleeve. It's only 5 millimeters thick. So it's going to cool pretty uniformly if I dip that into something cold, liquid nitrogen, or put it in a deep freezer. I can cool it pretty uniformly. It won't build up a lot of stress that might cause a crack. And we can just slip it in there. When it warms up, it expands and it's snug in there. So we grab our different materials formula, comes out with about 0.7 MPa for our interface pressure. Our interference is only 0.02 millimeters. So it's a really, really precise fit between these two. Once we have it in there, that's our interface pressure. Inner part pushes on the outer part pushes back the same on the. And this equation came from UI taken away from U outer equal to the delta, right? This expression and this put together was what got us our pressure because we started knowing what delta. So once we get the pressure, we go back and solve for the two displacements. I can see that my inner part in this case moves 0.018 millimeters, moves 90% of that gap, and only 0.002 millimeters, 2 micrometers does the hub. And this is certainly a case where we've got a really bulky hub part. It's 50 millimeters thick, and this is only 5 millimeters thick. So 10 times as thick, and it also has a higher modulus. So we expect that little sleeve to have to do more of the moving out of the way, and it does. Here's our alpha for the aluminum, and we've got our friction coefficient of 0.1. So when we're removing the part, we can just take our F install formula here, 2 pi r L, that's our soup can label area times pressure. So this is my normal force times mu gives me my friction. And that applies in the axial direction for frictional force, 3,200 newtons. So divide that by 5, it's about 600 pounds of install or removal force. So removal force there, pretty reasonable. We could do that with a press with a crank, like an arbor press kind of thing in a machine shop. Once it's on there, before it starts slipping, it'll carry this much torque, all right? We'd like it to either slip on the inboard or the outboard side so that the titanium part doesn't get grounded. All right. When it comes time to install the new one, we're doing the inner part, so we need to make it smaller. We just put a minus sign on the same formula. Delta T times alpha for the inner part is the strain. We want it to shrink. Times radius gives us our radial displacement, and then it has to equal the interference. And we come up, we only have to cool it by a little bit. So that won't even take a liquid nitrogen. We could probably just put it in the fridge down the hall in the break room at the depot. we can get it down by that much. It's maybe 15 degrees F delta. All right. And we can see that as it warms up, it expands. The aluminum will expand more than this. So on a hot day, the bearing will be snug up against the hub there. All right. So no chance of it falling out. On a colder day, the bearing is going to shrink faster than the hub, but then it's going to be snug on the pin that goes through. So it's always going to be hanging on one or the other, whether we're in a hot climate or cold. All right, anybody have any questions about the multi-material? Still just plug and chug. We just have a little bit longer formula for the pressure. All right. And the other thing to be careful of is when you're doing the solutions, we've got an E inner and an E outer. Right. On our other formulas was the same modulus here and here. So when you're putting it into your number crunching, just be sure you're cognizant of the individual material problem. Okay, same format for exam number 2. We'll come in Wednesday. I'll print a bunch. A few people will come and grab them, and other people will download them. But I'll have copies if you want to come in. So we'll see you guys Wednesday for the exam. And then we just got a little bit more, a couple more lectures on the energy and thermal stuff, and then we'll be done for this quarter.